We tend to think of our computers as magic boxes, where data just teleports instantly from one place to another. You click a mouse and the video plays. You press a key and the letter appears. The flowing data is not magic. It is a physical thing, usually an electric or optical signal, and because it is physical, it is bound by the ultimate traffic law of the universe, the speed of light. To really understand why modern computers look and act the way they do, we have to stop thinking about time as just a number of milliseconds or nanoseconds, and start thinking about it as a physical distance. To do that, we have to talk about a legendary computer scientist named Grace Hopper. Hopper was famous for having a brilliant way of explaining the physical limits of computing to people who didn't quite grasp the concept. When programmers would complain that the execution of their code was taking too long, or when military officers asked why satellite communications had a delay, she would reach into her pocket and hand them a piece of wire. Not a random piece of wire, but one cut to a very specific length, exactly 11.8 inches. Why 11.8 inches? Because that is the absolute maximum distance that light can travel in a vacuum in one single nanosecond. 1/1,000,000th of a second. If you want to do the math, you take the speed of light, which is almost 300 million meters per second, and divide it by 1/1,000,000th. You get right around 30 centimeters, or just under a foot for my overseas viewers. That little piece of wire was a physical representation of time. In the world of computing, a nanosecond is a rigid measure of physical space. Information physically cannot travel further than that 11.8-inch wire in that amount of time. The laws of physics absolutely forbid it, and truthfully, in an actual copper wire, electricity travels even slower than that due to the properties of the wire and its insulation, making the real-world distance even shorter. Every time your computer processes a piece of data, an electrical signal has to physically commute. It has to travel down a wire, bridge across a circuit board, and navigate the pathways of a processor. When you are just doing one calculation, you don't notice the commute. But as we are about to see, when you start building machines that need to do millions of calculations every second, the physical length of your wires suddenly becomes the biggest bottleneck you will have. Oh, and by the way, if you want to learn more about Grace Hopper and other women who significantly shaped computer science, I made a video just about that. So take that 11.8-inch wire and hold it in your mind. Now picture the pioneers of the 1940s and 50s, machines like ENIAC or early IBM mainframes. These computers did not sit on a desk. They took up entire rooms. Vacuum tubes, relay switches, and miles upon miles of copper wire. Think about what that massive scale means for our physical speed limit. Imagine you have a processing unit on one side of a room and the memory bank on the exact opposite side. To get them to talk to each other, engineers had to route thick bundles of cables beneath the floorboards or through the ceiling. Let's say that physical cable path is 40 feet long. We established that in perfect vacuum, light takes about 1 nanosecond to travel roughly 1 foot, but electricity traveling through a physical copper wire is actually slower. The signal propagation speed is usually only about 60 to 70% of the speed of light. That means our 40-foot cable doesn't just create a 40 nanosecond delay. Realistically, it is closer to a 60 or 70 nanosecond delay for a single pulse of data to make a one-way trip. 60 nanoseconds might sound incredibly fast to a human being, right? We can't even blink that fast, but to a computer, imagine trying to have a fast-paced conversation with someone, but every time you ask a question, you have to wait an hour for them to reply. That is what it felt like for the processor. It was just sitting there, bending power, doing absolutely nothing, waiting for the electrical signal to physically cross the room. If a simple mathematical instruction requires 10 back and forth trips between components just to add two numbers together, you are suddenly wasting hundreds of nanoseconds just on the commute. And when you want your machine to perform thousands or millions of operations a second, That travel time rapidly piles up into a massive traffic jam. Early hardware design had essentially become its own worst enemy. Engineers were building these incredibly complex, imposing machines, assuming that bigger meant better. But they were discovering a harsh truth. The sheer physical geography of the machine was exactly what was ultimately choking its performance. This brings us to one of the most crucial turning points in the history of computer science. The engineers realized they had hit a wall, and it wasn't a software wall, it was a physical wall. For a long time, the assumption was that if you wanted a more powerful computer, you just needed to build a bigger one, add more vacuum tubes, add more memory cabinets, write clever algorithms. It's not completely wrong, especially with the algorithms, but the physics simply didn't care how clever the code was. If a signal has to travel down 20 feet of cable, it is going to take time. You cannot negotiate with the speed of light. Imagine an incredibly fast, highly optimized piece of software running on one of these mainframes. The algorithm knows exactly what it needs to do, but it just keeps slamming into a physical barrier. No matter how brilliantly that software is written, if the hardware dictates that the electrical pulse has to commute across a room, the software is eternally trapped, waiting for it. This was the paradigm shift, the ultimate engineering realization that if you wanted to make a computer faster, you could not build it bigger. In fact, you had to do the exact opposite. Big machines are inherently unavoidably slow machines. To beat the clock and squeeze more calculations into every passing second, there was only one possible solution. You had to beat the physical distance. The entire industry realized that the future of computing really wasn't about expanding outward, it was about shrinking inward. So the industry did what seemed like the wrong way just a moment ago. They took these massive humming rooms full of glass vacuum tubes and miles of heavy copper wire, and they shrank them down, way down. They swapped the bulky tubes for microscopic transistors, and they etched the connecting pathways directly onto tiny wafers of silicon. By shrinking the components to a fraction of a millimeter, they completely solved the micro-distance problem. We no longer had to send electrical signals 40 feet across a room. We were sending them 40 micrometers across a chip. This extreme reduction in physical space is the entire secret to modern computing. It is exactly what allows your current phone or laptop, to operate at speeds measured in gigahertz. Let's break down that word. A hertz is just 1 cycle per second. A gigahertz means 1 billion cycles per second. If you have a processor running at 3 GHz, it is completing 3 billion block cycles every single second. That means the computer has exactly 1/3 of a nanosecond to execute an instruction before the clock ticks again. Think back to Grace Hopper's 11.8-inch wire. If a signal can only travel about a foot in one whole nanosecond, in 1/3 of a nanosecond, it can barely travel 4 inches. If your computer's memory and processor were just 5 inches apart, it would physically fail to run at 3 GHz. The signal simply wouldn't arrive in time to catch the next clock cycle. But because a modern silicon microchip sits effortlessly on the tip of your fingernail, the distance the data has to travel is practically zero. The electrical signals don't have a commute anymore. We didn't just invent better materials or write smarter software. We engineered our way around the fundamental speed limit of the universe, simply by making the racetrack microscopic. There's actually one more layer to this story that makes for a perfect cherry on top. We solved the distance problem inside the computer by shrinking the chips, but we still have to send data between computers across the globe. And suddenly, Grace Hopper's wire matters again, but on a massive scale. Think about the global financial markets. In high-frequency trading, algorithms buy and sell stocks in fractions of a millisecond. If your trading server is in Chicago and the stock exchange data center is in New Jersey, your data has to physically travel through roughly 800 miles of fiber optic cable. Even at the speed of light, the journey takes a few milliseconds. In the world of algorithmic trading, being a millisecond late means a possibility of losing millions of dollars. Because of this undeniable physical speed limit, financial firms have literally spent hundreds of millions of dollars to lay new fiber optic cable in perfectly straight lines between cities. They have paid to tunnel directly through mountains rather than going around them, just to shave a single millisecond of the data's commute. They even buy real estate right across the street from the stock exchange data center, paying a massive premium just to use a physically shorter cable. So while our processors have shrunk down on the microscopic level, the absolute speed limit of the universe is still dictating the shape of our world. It dictates where we build our networks, how we lay our cables, and serve as constant reminder that no matter how advanced our technology gets, data still has to physically travel through space. That would be all for today. If you like the channel and would like to support it, consider membership, or of course, like, comment and subscribe. As telegraphed at the beginning, here you can watch a video summarizing 3 women of computer science and their forming impact on the whole industry, including Grace Hopper. Thanks for watching. I hope you learned something interesting today, and ciao!